A way to get an interference pattern with just one light source is using an arrangement called Lloyd's mirror. You use a mirror surface to reflect part of the beam, and at the viewing screen, the direct beam interferes with the reflected beam. You can treat it as 2-point sources, with the reflected beam treated as if it came from a virtual source under the mirror. The one thing you have to take into account with this pattern is that the pattern actually has maxima and minima reversed from what they would be from two real sources, and that is because there will be a phase change when the beam gets reflected. So phase change is something we'll look at now before we get on to interference in thin films. Now, remembering back to waves travelling along strings. If a wave is travelling along a string and reflects from a fixed end, the reflected wave is upside down. In terms of the equation for the wave, this is a 180-degree phase change. The same thing happens when light travelling through a low refractive index reflects off a boundary with a higher refractive index material. But if the wave on the string reflects off a free end of the string, the return pulse is the same way up as the incident pulse. There has been no phase change. In the same way, a light beam travelling through a high refractive index reflects off a boundary with a lower refractive index material with 0 phase change. Let's look at it happening to see what this means. Here we see two waves approaching an end of the string, and one end is fixed, but at the bottom it's an end that is free. And when you see the reflection from the fixed end, the wave is now upside down. From the free end, the wave is right way up. And now you see a wave on a string approaching a change in medium, going to a higher density medium. Now you can see here that the reflected wave was reversed, so the reflected wave had a phase shift, but the transmitted wave that you can just see in the distance hasn't had a phase shift. We've all seen the iridescence of thin films, such as soap bubbles or oil floating on water. That's also what we see in the butterfly and the bird that we had right at the beginning of the lesson. These patterns are made when interference happens between light beams reflecting off two surfaces of a film. Because thin films are often materials of various refractive indices, we have to take that into account when we work out path length differences. We know from refraction that speed is less in a higher refractive index, and so wavelength, which is proportional to speed when frequency is constant, will be less as well. So if two rays start out in phase but go through two different mediums, one will be more slowed down than the other because its wavelengths are shorter. We include that in our interference equations by making sure that rather than just using wavelength, as we did in Young's experiment that was in air, we have to take wavelength divided by refractive index. The path length difference creates a phase shift, and the phase shift phi is the same fraction of 2 pi as the path length difference is of one wavelength. So we can write phi over 2 pi equals path length difference over lambda, and hence the phase shift phi is 2 pi over lambda times the path length difference.